You're welcome to the section on logarithms. We looked at indices in the previous lecture video, and we got to appreciate indexes written this way. We said this means I can multiply a by itself x times to give me some number n. So if I know 2 to the power 3 means I'm multiplying 2 3 times to give me 8. N is known, a is known, and then x is this 3. But there are instances where I might not even know my x, but I know my n. It means I'm looking for this guy. How do I find this 3? So n is known, and then a is known. Now your n becomes your argument or the answer argument. Your a we already know is your base, and what you're looking for, this is the unknown. What you're looking for is your index. To find that, we simply take the logarithm of your base with respect to your argument. Let me take that again. So from this preamble, I hope that is well understood. If my argument is known, my base is known, what is my index? It says take the log of your base, so we say log n base a. N is your argument. That is how you find your index x, and that is the introduction to logarithm. So it's like this moves here with respect to log. So look at the example here. 2 to the power x is giving me some 5. What is x? Sorry for this. My n is known. To find x, I simply take the log of my 2, log of my 5 to the base here 2, and that is my x. And that is the introduction to logarithm. So it has a relationship with indices. I hope that is well understood. The same way we looked at indices application with the rules, we have the same thing with logarithm. So let's look at the log rules. I'd want to clean this part. The first rule is that if I have the argument and the base being the same, it is simply 1. No need to argue out this. There are proofs for this. If you use your calculator, you can verify this. So the rule is, if the base and then the argument are the same, the answer is 1. Now if the argument is 1, it is 0. Please, it is not when the argument is 2, it is 0. No, anything aside 1, it is not 0. So log of 10 is not 0. But when you have a base given and it is 1, that is where it is 0. So take note of the second rule. The third rule says that I have a log, but the argument is now, all the logs are with some base a. So let me just quickly add where there's no a. Now my n is some m to the power p. It means the n is raised to some power this. I can rewrite it that way. I hope I'm not confusing you. Okay. Now the argument has another index, p. It says just bring the p down and then take your log of whatever is left. Then next, so I'm done with this. That. Now let's come to here. This is a consequence of this law. How? I have log a 1 over n. I can rewrite this as log a n to the power negative 1. And what does the rule of the power index say? It says if you have something above, bring it out. So negative 1 log a n. Is that what we have here? Yes. So that is just the consequence of it. I didn't bring the a. Now the fifth one says if you have two arguments multiplying itself together, just add them. Multiplication leads to addition, just as the indices. The next rule says, we've already established this from up here is just this guys here. So log a of m equal to n. If I want to find m, it's just taking the a to the power that we've established this. And let's look at this next one. If I have a base and a log raised to a log, it is simply the m. These are common rules we can play along. Now the interesting part is the last rule. We call this change of base, so I think I can clear this. It is called a change of base rule. There are instances where you want to solve the problem by introducing another base. So look at it. The original base was a, but now the new base is c of b and then a. This c is called a common divisor. My writing is becoming bad, forgive me for that. That is a c. You find common denominator between your base and then the argument, and you can use the change of base to solve it. Now there are some logs we can't find. Let me use red to emphasize that. A log of a negative number does not exist. A log of 0 does not exist. So that's why I use the cross sign here. So log negative 25, you can use a calculator. It does not exist. So you take note of these ones. Okay. So let's quickly move to examples here. I think I'll go straight to slide 9 for my examples. Okay. Log 10 base 10. From the property of the base and an argument be the same, so this simply gives me 1. I know you can use a calculator to do this, but I want to employ or know what the calculator is doing, and that is what it is applying. I have a base 3 and argument 9. I can rewrite this as 3 squared. But I know log 3 is like this has a power, so I bring the 2 down and I have log 3 base 3. This simply gives me 1, and hence I have the answer as 2 by the power index. Okay. Now the third example, so example 1, example 2, example 3, log 8 base 16 equal to some x. I can use calculator. I know you cannot use calculator. If I want to find this, I simply have to find a log. What am I even saying? Yeah, so I'm setting log 8 base 16 to some x, and I can simply rewrite it as the index form by the property. I know 8 is 2 to the power 3. It means I have to find a number 2 to the power something such that I can compare them. Now because the base are the same, we go back to indices. 2 to the power 4, 2 to the power 3. Because they are the same, I can simply compare them. By indices, I can expand this bracket. So you see where we are moving from. So if I compare, this what I have, and simply s becomes that. Let's look at the last 3. We want to employ the negative or the difference. As far as the base are the same, I can simply divide them, and I use my calculator. I'm good to go. If I'm adding them, as far as the base are the same, is the base we are interested in. If they are not the same, please, you compute them differently. If they are the same, it says you can simply multiply the argument, just as we did in indices, and so on and so forth. Now I want to look at the change of base example. I think that will be my slide 10. I know, let me check slide 11. Yeah, change of base. We are looking for the common divisor. So look at the first example. I have a base of 8. This is the base, and this is the argument 2. The common divisor here can only be 2 and not 4. You know that. And so I introduce a common divisor here and then here. Now you realize that log 2 base 2 is 1 from the property. And here I can have it as log 2 to the power 3. So here becomes 1 and I get 1 on 3. Okay. If I don't want to use the common divisor or the change of base, whatever approach I use, I'll get the same answer. The next example, log 125 base 5. The common divisor of 125 and then 5 is simply 5 and nothing else. So I introduce a 5 here and then the 5 here. If I want to simplify further, you'll realize that the divisor here gives me 1. What about the numerator? I don't know what I did here. The numerator is the same as log 5 to the power, I think 3. By the properties or the rules, I have 3 log 5 to the power base 5, and then I have log 5. This is simply 3 over 1, and the answer is 3, and you are good to go. Some will say, why would I want to bother with a change of base? It comes handy sometimes. Or you can simply solve this one straight away. I know log 5 is 5 to the power 3 here for the 152. Why did I say 152? 125. And so I simply get 3 log 5, which is 3 times 1. I mean, you have to know all the techniques such that when they become handy, you know what to do. So that's the way the common base approach. I've solved the 2 examples. Now the interesting aspect of my lectures is the problem of the day. I want you to appreciate what you do with all that you've learned. I guess I've been very quick with this session, but you take your time and then play the video again and then you get it. We are performing a scientific experiment for a reaction, rate of reaction. Whether you're in biology, you're in any of the science related field, you come across this reaction or rate of change. It says it is governed by some equation. I always tell you, when you see a word problem, there are some things you want to extract. So here we have extracted our equation. It has some terms which are being defined. R, C, K's are defined. Now to the problem, what are we requested to do? We are asked to simplify the equation by expressing R in terms of C and K. So we are looking for some relationship between R, C, and K. Scientifically, we know rate of reaction decreases with respect to time because of our molecules, reactions, and stuff. I don't want to go into details. But let's look at the problem. How does this, guys, relate? Please, let's go back to the equation here. You want to employ the rules of the game. Do you remember this rule? If I go back to my slides, the log of the differences here means just take the division because the base are the same. I can divide. So if I rewrite this, guys, as my 2 log 10, my 2 log C base 10, and I rewrite this one as my log K base 10, does it mean that I have the answer as log 10 2C over K? That is the question. Is this the answer? You realize that no, it can only be the answer if there was no 2 here. They could simply take the division and say, hey, R is equal to C on K. But there's 2 there, so we have to employ this rule. So you go back to the slides, remember this rule. If the argument is raised to another index, it says take the index out and then evaluate the remaining logarithm. So what is the P in this question? The P is 2 log 10C. then I can come back and then say that my log 10r is equal to, now it means that this is the same as that. Forgive me if this is messing up, but it's easy to follow. My 2 log 10, is it minus or plus? Minus log k10. This the same as writing it as log 10c squared minus log 10k. So with the question, what is r? What is the relationship now here? It means I cannot take the division. If I do away with the log 10s, what is the relation of r and then k? Give me the answer in the comment section. Take your time and go through this, and then you verify, or you can see the answer. Now the second question is, if c is that and k is that, what is r? You realize that the problem 2 depends on what you get here. If this answer is wrong, because you simply have to substitute the value for c and then k. So assuming the answer is c squared on k, no, I'm not sure that is the answer. If I go back to the very first thing I wanted to do, I would have said the answer is 2c on k, and I would have substituted my value for c and then my k as 5, and I'll get my r. So it's 2 depends on 1. I want you to provide a relation of r in the comment section for me, and then the final answer for r when c and k are being substituted. In the next section, I'll look at the natural logarithm, and that'll be the last lecture video on indices and log. Thank you.